Okay, so in this video, I'm going to talk about more properties of the polyspin matrices. And just to recap, these matrices are, oops, so this is going to be our choice of the matrices. Okay. Now it doesn't have to be, but this is the choice that we're going to use. So the next property, this one is property number 5. And so if we combine property number 1, which says the anti-commutation relation is equal to 0. Now this is going to only be true if I is not equal to j. And then property number, what was it? Property number 4, which basically said if they are the same, if you square them, then you get the identity matrix. If we put those both together, then what we get is a more general anti-commutation relation, which says it's equal to 2 the delta function times the identity. So of course, if I is not equal to j, I not equal to j, then the delta function is going to be 0. And if I is equal to j, then the delta function is not going to be 0. It's going to be 1. So your choices are 1 or 0. So now what we have is a more general equation for the anti-commutation relation right here. The next property says that if I have, say I have two vectors, so if vector A commutes, oh, I'm sorry, not commute, yeah, if vector A commutes with sigma and vector B commutes with sigma, so I have these two vectors that commute with the spin matrices, then I could write down this equation where A dotted into sigma, so that dot product, times B dotted into sigma. I can write that as A dotted into B times the identity plus I A crossed into B dotted into sigma. So basically, if you work out this one vector identity, what you get is basically the dot product of A and B plus another term, which is kind of like these cross terms with sigma. Okay, so one more property, property 7. So now if I combine a bunch of these other properties, so one is the product. So remember that's I times the sum, Levi-Civita times the spin poly, the poly spin matrix, and the trace of any matrix is 0, and any matrix squared is equal to the identity. Now I can write down that for I not equal to j, then I have the trace of the product of any two matrices is going to be equal to I times the sum the trace of that Pauli spin matrix. So I can combine this to show that I can basically combine the first statement up here with this statement, the trace, and I come up with now the trace of the products, not the trace of just one, but the trace of the product of two, is this sum. If now, so if we try when I is equal to j, then what we get is sigma I, sigma j is equal to sigma I squared. The trace of sigma I squared is just the trace of the identity, which is now 2. So that gives me the trace of any two, the product of any two Pauli spin matrices is equal to 2 times the delta function. So let's say we come up with a fourth Pauli spin matrix. We'll call this sigma sub 0, and we're going to set that equal to the identity. So now what we have is the trace of the product of any of these four. So I'm going to switch from I and j to alpha and beta. So now I can, that's going to be equal to 2 times the delta function, alpha beta, where now both alpha and beta can be either x, y, z, or 0. So I've added a fourth matrix, so that the identity matrix now actually can be included in the list of the Pauli matrices. So we have the 3 that are related to spin, and then 1, which is just the identity itself. So what this actually, this last property, what it works out to is that all of these Pauli matrices, so now I'll say sub alpha, because we can go from 0, 1, 2, and 3, if you want to call x1, y2, and z3. So over the 4 indexes, 4 indices, then that means that they're all of these are linearly independent of each other. So that means that I can't make any of them out of the others. I could not write down, say, sigma x, which is some constant a times sigma y, plus a constant b times sigma z, plus a constant c times sigma 0. I can't, with the 4 matrices now, I can't write them down as a linear combination of each other. So this statement right here is not true. All of them are independent of each other. So these 4 matrices, so the 4 matrices that we have now, sigma x, sigma y, sigma z, and the identity, sigma 0, are the minimum for a basis. So now these are the 4, with these 4 matrices, we can now write down a basis for spin. Now we could make some other function which is a combination of these 4 matrices, So, I mean, we can make other matrices which are built out of the Pauli spin matrices, but I can't write any of the four in terms of the other. They're all independent of each other. So to kind of show you that, so now we'll build a state, let's say, or a matrix, or not a state. So I'll build a operator out of the sigmas. So I can have an operator M, which is now the sum of some constant M sub alpha times the four matrices. So this right here are just constants, just factors, which shift the Pauli spin matrices. So really the last question is, how do we get those constants M sub alpha? How are we going to find out what they are? So what we can start with is we'll take the operator M and we will operate in conjunction with one of the Pauli spin matrices, sub beta, sigma sub beta, which is now the sum over alpha, M sub alpha, sigma beta. So that just gets pulled into the summation. If I now take the trace of this, like so, I can now bring the trace inside the summation. So I'm now taking the trace of the product of those two spin matrices, but I've already worked out what the trace is going to be. So the sum of alpha is M sub alpha times 2 times the delta function of alpha and beta. And so if I remember, if this was, say it was the sum of 4 of them, that would be M0, 2, 0 beta plus MX 2 delta X beta plus MY 2 delta Y beta plus MZ times 2 delta Z beta. So in this case, all three of them are going to be equal to 0. And I'm only going to save the one term, so the delta only is 1 if one of these 4 is equal to beta. So basically, delta alpha beta is only equal to 1 when alpha is equal to beta. So in the end, what I get is 2 times the constant beta. So I can pull out the one that I want. So in the end, my M sub beta is equal to 1/2 the trace of whatever function I created, M, times sigma times beta. So if I create this function M, and I want to figure out what the constant M sub x is going to be, then I would just have M sub x is 1/2 the trace of my operator that I created times sigma x. And from that, I could then calculate basically all 4 m's that give me the linear combination to create this new operator, capital M.